we are glad to present our work Uncertainty-Driven Dense Two-View Structure from Motion. Structure from motion, or SFM, is a long-studied problem. Its objective is to take a set of 2D images and recover the camera pose for each view, as well as reconstruct the 3D scene geometry. It's worth noting that reliable solutions for SFM currently available are mostly sparse. Yet, the challenge of achieving a reliable dense SFM persists and remains a significant open problem. This is required by downstream tasks in fields like robotics, autonomous driving, and mixed reality. Importantly, the success of large-scale sparse SFM and visual SLAM systems is rooted in the robust theory of two-view SFM. Therefore, we want to start solving reliable dense SFM from a two-view approach. For the dense two-view SFM problem, we take two RGB images and the approximate estimates of per pixel correspondence as input. From this, we determine the relative camera pose and dense 3D geometry. Traditional methods are usually based on two-view geometry and focus on feature extraction and feature matching. While the Ransack algorithm can be employed to robustly estimate the camera pose, it is hard to obtain the dense geometry. In comparison, learning-based approaches utilize neural networks to regress both pose and depth. Although these can be trained end-to-end to leverage dense pixel information, they often demonstrate poor generalization in novel scenes, particularly when faced with occlusions and dynamic objects. Hence, in this work, we focus on leveraging uncertainty for two-view dense SFM. For pose estimation, theoretically, we only need 5 reliable pairs of correspondences under certain conditions. However, real-world scenarios present challenges such as matching filtering, the zero-flow problem, and correspondence distribution. Introducing uncertainty enables us to detect and filter out ambiguous matchings, thereby enhancing accuracy. Besides, dense 3D structure recovery requires dense matching between two views. Perfect dense correspondence, however, is often hard to obtain. Again, by incorporating uncertainty, we can reason about per-matching confidence, ensuring we obtain a reliable subset of correspondence. In our pipeline, given two input images, we first estimate forward-backward dense optical flow correspondences and their per-pixel uncertainty using optical flow networks. We then compute the relative camera pose using weighted bundle adjustment, which considers learning-based flow uncertainty, robust outlier filtering from Ransack, and bidirectional flow consistency. Next, we employ the relative pose to estimate the depth of the reference image, using an independent module that balances both monocular and cross-view cues. The estimated depth, combined with the predicted pose, facilitates iterative refinement through geometric consistency. We conduct extensive experiments to demonstrate the effectiveness of our methods. Firstly, we compare our camera pose estimation with existing two-view SFM methods on the RGBD dataset and achieve significant improvements in both translation and rotation accuracy. Numerically, we compare our methods on benchmark datasets, including YFCC 100 million outdoor dataset and ScanNet indoor dataset. Our method has significant improvement in the camera pose accuracy, with a 21% gain on YFCC and a 19% gain on ScanNet. Compared to the pure Ransack approach, our uncertainty-driven pipeline yields more accurate pose estimations. Qualitatively, we can also observe that our estimated 3D reconstruction is more consistent with the scene geometry, compared to the existing methods like deep SFM or single-image depth estimation (MIDAS). So the final takeaway from our approach is that for pose estimation on dense correspondence, it is quite intuitive to use an uncertainty-driven approach to get reliable pose estimates. And by exploring the geometric consistency between pose, depth, and dense correspondence, we can further enhance the performance via iterative refinement. Thank you.